Thanks to Andre for inviting me to give this talk. These are some of our papers published on this topic. These are my co-authors down here. Our book, published with Oxford, 2024, blurbed by Adlam and Bruckner, Boob, and Wharton, is on the table in the back if you want to check that out. Okay, first a historical context. That would be Einstein's reconstruction of the Lorentz transformation kinematics of Maxwell's equations in response to the experimental situation in the late 1800s. Of course, most famously, Michelson-Morley experiment. They rotate their interferometer throughout the day on different days through the year, and they never see any change in the interference pattern, which they take to mean people are going to measure the same value for the speed of light c, regardless of their motion through the luminiferous ether. So they have the common understanding at that time was the luminiferous ether is a causal mechanism that shrinks objects in the direction of motion through the ether. That fools everyone into measuring the same value for the speed of light, and that gives you your Lorentz transformations. So length contraction is a dynamical effect due to some causal mechanism, right? That's a constructive explanation taken from Einstein's notion of constructive theories. Constructive theories are those that explain phenomena as dynamical effects due to causal mechanisms. Like the kinetic theory of gases explains temperature as the mean kinetic energy, right, the molecules of the gas. Einstein himself tried constructive efforts, he said, for about 5 years before he gave up, writing, by and by I despaired of the possibility of discovering the true laws by means of constructive efforts based on known facts. The longer and the more despairingly I tried, the more I came to the conviction that only the discovery of a universal formal principle could lead us to assured results. So he was looking for a principal explanation, analogous to his idea of a principal theory. A principal theory of those whose formalism is derived from some empirically discovered fact. Thermodynamics, for example, comes from the universally experienced fact that perpetual motion is impossible. In a principal explanation, you have some compelling fundamental principle justifying your empirically discovered fact, which dictates your kinematics, solving a mystery. So Einstein said, well, look, the relativity principle with Maxwell's equations dictate the observer independence of c, his light postulate, whence the Lorentz transformations requiring length contraction. So in this principal explanation, length contraction is not a dynamical effect due to some causal mechanism. Length contraction is a kinematic fact necessitated by the relativity principle. What was Lorentz's response? Well, first, he complains, look, Einstein simply postulates what we have deduced with some difficulty and not altogether satisfactorily from the fundamental equations of the electromagnetic field. In other words, Albert, you can't reconstruct my transformations from the light postulate. The observer independence of c, that's what we want to have explained. You can't use it to do the explaining. It's an explanandum, not an explanans, right? But then he does admit, look, by doing so, Einstein may certainly take credit for making us see in the negative result of experiments like those of Michelson, Rayleigh, and Brace, not a fortuitous compensation of opposing effects, but the manifestation of a general and fundamental principle. So, because he justified the light postulate with the relativity principle, Lorentz said, all right, I'll let it slide, right? And today, 120 years later, we don't have any constructive counterpart to this principle, right? Reconstruction, Lorentz transformations. So here's, for example, an introduction to special relativity from Knight in his 2022 text. Starts with the relativity principle, which we call no preferred reference frame, or NPRF for short, and says, all right, according to the relativity principle, Maxwell's equations are true in all inertial reference frames. They tell us this is the speed of light c, therefore everybody has to measure that speed of light, right? Here's Rex and Wolfson. They have the same argument in their 2021 text. This is Young and Friedman. They have the same argument in their 2020 text. If you want these slides, by the way, to read all the stuff, just email me and I'll send you a PDF. Surway and Jewett in their 2019 text. Here you can see postulate 2 is required by postulate 1. John Norton in his 2024 course on special relativity. If the principle of relativity was applied to Maxwell's law about light, the light postulate resolved it immediately. So, special relativity is a principal theory, in particular one that provides a principal explanation, and we denote it by NPRF plus C for short. Now let's go on to quantum mechanics. Fuchs writes, where present-day quantum foundation studies have stagnated in the stream of history is not so unlike where the physics of length contraction and time dilation stood before Einstein's paper on special relativity. He was motivated by this 1996 challenge from Ravelli. Quantum mechanics will cease to look puzzling only when we will be able to derive the formalism of the theory from a set of simple physical assertions, postulates, principles about the world. Therefore, we should not try to append a reasonable interpretation to the quantum mechanics formalism, but rather to derive the formalism from a set of experimentally motivated postulates. Obviously, his experimentally motivated postulates correspond to Einstein's empirically discovered facts, right? And he was himself motivated by Einstein's reconstruction of the Lorentz transformations, which he points out here existed before Einstein's 1905 paper. So what was Einstein's contribution? It was to understand the physical meaning of the Lorentz transformations. All right, so Ravelli's challenge was reconstruct the Hilbert space kinematics of quantum mechanics, just like Einstein reconstructed the Lorentz transformation kinematics of Maxwell's equations, right? Goyal points out, reconstructions like this in physics are common. Lagrangian mechanics, for example, is just a reconstruction of Newtonian mechanics. And I was hoping Greg was going to show up. Here's Greg's paper. As Greg points out, this idea of reconstructing quantum mechanics goes much farther back than Ravelli's 1996. Greg, back in the 1920s, right? Yeah. And Heisenberg himself even suggested reconstructing, back in the 1920s. So I'm only going to talk about those reconstructions that were motivated by Ravelli's challenge. And it's generally agreed that Hardy was the first to come up with a successful answer to Ravelli's challenge with his 2001 paper, Quantum Theory from 5 Reasonable Axioms. Since then, many of these so-called axiomatic reconstructions of quantum mechanics based on information-theoretic principles have been published. Here's a sample from references in one of our papers. Marcus Mueller points out references 10 and 11 are, quote, the first fully rigorous complete reconstructions. But if you'll notice, those were published in 2011. That was 15 years ago. So if they have successfully answered Ravelli's challenge, why doesn't everybody say, oh, well, now quantum mechanics, perfectly clear. We understand special relativity. Now we understand quantum mechanics, right? Clearly something is missing. And here's a common complaint in quantum foundations. Nothing additional has been shown to be incorporated into an information-theoretic reformulation of quantum mechanics beyond what is contained in quantum mechanics itself. In particular, it's not giving us any more unification. And that's generally what you expect from a principal theory. Since it's not giving you any causal mechanisms, what is it giving you? Typically, it gives you more unification. But as Van Kamp points out, well, a reconstruction isn't. You're just taking the formalism and you turned it around and reordered it in some way, right? What are we getting? So something is clearly missing. And let's go back to see what that's missing. Let's go look at Dergell's reconstruction. He starts with the reconstruction with discreteness requirement. The reconstructions are, of course, start with the qubit, the quantum information bit, and then they build up to Hilbert space. We don't have to do any of that stuff. All we got to figure out is this starting point to justify what else the mathematicians have done with their reconstructions. So let's look at Dergell's starting point here. So, and he's going to do the physical instantiation of the qubit is spin a half. That's common. You have polarization, double slit, Mach center, whatever, however you want to do it. But we'll do spin a half. It's easiest to see what's going on here. All right, there is a continuous infinity of possible measurements of a spin, but there are only 2 possible outcomes for each measurement, plus or minus h bar over 2. I'll typically just say plus or minus 1, right? And he points out, and if I know I have a state in particular directions, say plus 1, and then I measure it over here at beta, I still just keep getting plus or minus 1. I don't get the fraction of the outcome that we expect. This is the first of the stuff I've taken from Andre's book, whenever I say I got from Andre's book, I'm talking about his newest book right here, Contextual Reinterpretation from.
I took this from Arkady's book.
This is actually a hybrid quote. Some of this is Andre, and then some of it is a direct quote from Bohr. This reads nicely this way. The essence of quantum theory may be expressed in the so-called quantum postulate, which attributes to any atomic process an essential discontinuity, rather individuality, completely foreign to the classical theories, and symbolized by Planck's quantum of action. All right. Again, you measure the electron spin with Stern-Gerlach magnets, you get plus or minus 1, nothing in between. All right, so this is Derridel's discreteness requirement, his empirically discovered fact, or his experimentally motivated postulate, right, at the beginning of his Reconstruction. Now let's see how he uses that to derive the spin-a-half qubit probabilities. He starts with a state size z plus, make a measurement at b hat, make an angle beta with respect there too, and what do you expect to get? Well, it's an angular momentum, right? Newtonian mechanics says if you know you have an angular momentum plus 1 z hat, and you measure it in the b hat direction, you should just get plus 1 cosine beta, right? But you can't get anything other than plus or minus 1 due to discreteness. So we recover plus or minus plus cosine beta on average, quote, in order that the average angular momentum in the direction beta be equal to the projection of the initial angular momentum on this direction. This is so because, by a correspondence argument, a large number of identically prepared, not interacting spin particles should behave as the angular momentum of a macroscopic object under measurement. This is Derridel's correspondence requirement. Dacke and Bruckner call this the closeness requirement. Comte calls this the homogeneity of statistical ensembles. All right, so with discreteness and correspondence, you have this average-only projection equation, that with normalization, and there's your spin-a-half qubit probabilities. And this is as mathematical as it gets, by the way. I'm sorry. All the morning you've been seeing all those highly mathematical talks. This is all the math you're going to see at this level right here. So discreteness and correspondence give you qubit superposition. Bruckner and Zeilinger's counterpart to discreteness and correspondence is information invariance and continuity. The total information of one bit is invariant under a continuous change between different complete sets of mutually complementary measurements. In other words, looking back at what Derrida did, you have your spin state psi equals z plus. Your qubit of information is that if I make a z hat measurement on that state, I will, with 100% certainty, get plus 1 as my answer. And then as I make my measurement b hat, continuously varying it at 100, 0 goes to 90, 10, 80, 20, right? So that corresponds to the total information of one bit is invariant under a continuous change, measurement direction b hat. You get to 90 degrees, then you totally randomize your initial piece of information. It's 50-50 outcomes. That's called your complementary measurement. And you have x hat and y hat corresponding to z hat, giving you your complete set of mutually complementary SC measurements. You can do the same with b hat, and that gives you the second half of their information invariance and continuity between different complete sets of mutually complementary measurement. This is a figure from Bruckner and Zeilinger's paper to show you that. The two reference frames rotated with respect to each other by beta. All right. So discreteness and correspondence, that's equal to information invariance and continuity from Bruckner and Zeilinger. All right, so what's wrong with these, what's missing? What's wrong with these reconstructions? Well, Derrida himself points to the problem right here. From a physical point of view, discreteness is a non-trivial assumption. In the present state of this approach, we should probably content ourselves with the insight that discreteness, this quantum discontinuity, and correspondence necessarily lead to quantum mechanics as we know it. In other words, we can't justify discreteness, but that and correspondence do give us qubit superposition and quantum mechanics as we know it, so maybe the end just has to justify the means? But that's totally equivalent to having Einstein derive or reconstruct the Lorentz transformations from the light postulate without justifying the light postulate with the relativity principle. No one, right? Lorentz, remember Lorentz was like, Albert, come on, that's bullshit. You can't derive Lorentz transformations from the light postulate. But he only bought it because it was justified. That would be like him not justifying it, right? No one's buying it. That's what's missing. That's what we need. We need a justification for discreteness. All right. So again, when you do your measurement, as Weinberg points out, of spins with certain Gerlach magnets, right, you're always getting plus or minus h bar over 2, so you are measuring a universal constant of nature, Planck's constant. So with that view in mind, we can look at the discreteness requirement and say, well, that's just entails the observer independence of Planck's constant h between inertial reference frames related by spatial rotations, or what Andre calls different experimental contexts. And in fact, that's exactly the way that Andre characterizes discreteness with his quantum action invariance principle. Andre, you stepped out right when you're coming up here with your picture and everything. The quantum of action is the same for all observers regardless of experimental context. This principle is the epistemic counterpart to Bohr's quantum postulate. So Andre has quantum action invariance and complementarity. So Dergel has discreteness and correspondence. Bruckner and Zeilinger have information invariance and continuity. And Andre has quantum action invariance and complementarity for the basis of their reconstructions. And as you'll see shortly, Andre's statement here from his book again is spot on. Personally, I think that quantum physics cries not for an explanation of the long-distance correlations and the violation of the Bell inequalities, but of the existence in nature of the indivisible quantum of action. Right? That's what we understand now. That's quite clear. We've got to figure out, why do we have discreteness? Now, everything I've shown you in the narrative thus far is from somebody else. This is not from our research group or our publications at all. This is our suggested big contribution, which we think is trivially obvious. Why don't we justify discreteness with the relativity principle and Planck's radiation law? Right? This is what I showed you before, Introduction to Special Relativity. Why can't you just introduce quantum mechanics in those textbooks like exactly the same way here? Say the relativity principle tells you that Planck's radiation law has to be true in all inertial reference frames. Planck's radiation law gives you this constant h with a particular value. Therefore, in all inertial reference frames, you've got to get h. When you rotate your Stern-Gerlach, you can't get a fractional value of h. It'd be like saying, I'm standing next to a light source, the beam comes out, I measure its speed to be c. I move along the beam, and I get a third of c, a half of c. No, you keep getting c. Right? So you have a 1 here, you measure over here, I should get a fraction of 1. No, you keep getting 1 plus or minus 1. So, it seems innocuous, but you see how it leads to qubit superposition, complementarity, and I'll show you in a second how it leads to your Bell state joint probabilities as well. All right, so we're saying they've produced quantum mechanics as a principal theory. They showed how its formalism follows from an empirically discovered fact, right? We're saying, why don't we turn it into a principal explanation, just like special relativity, and then we'll denote it by MPRF plus H. So, the relativity principle justifies observer independence of H. Andre calls it a quantum action invariance. That gives you your Hilbert space kinematics for quantum mechanics, right, which requires qubit superposition. So, qubit superposition, just like length contraction, is a kinematic fact. It's necessitated by the relativity principle. All right, now let's look at Dergel's reconstruction, or derivation, the joint probabilities for the Bell states. Alice measures at A hat and Bob at B hat. Here's your Bell state correlation functions. Dergel did for the singlet state. We'll do here one of the triplet states in the symmetry plane, right? So like, for example, this first one here, the symmetry plane is the XY plane, the generator is sigma z. And so again, we're looking for the joint probabilities to give rise to these correlations. All right, if you measure, Alice and Bob make the same measurement in the symmetry plane for a triplet state, they get the same outcomes. Dergel calls that his conservation requirement. So, when Bob measures off an angle theta, Alice says, well look, I know if he measured my direction, when I'm getting plus or minus 1, he'd be getting plus or minus 1. So he's off in that direction theta, he should be getting plus or minus cosine theta. But of course, discreteness says, no, he has to get plus or minus 1. So correspondence tells Alice to write down these average-only conservation equations for Bob's results from her perspective. Of course, Bob can make the exact same claim about her, right? Every perspective is equivalent. So he writes down these two equations, average-only conservation equations, for Alice's results from his perspective. So we see that discreteness, correspondence, and conservation give us these average-only conservation equations, and those with normalization give us our spin a half, joint probabilities, for our Bell spin states. All right, so this is where, what Andre had said before. Where's the real mystery here? Andre's pointing out in that quote, it's not here, not this point, it's way back here. Here's the real mystery. If you know what's going on here, then the rest of this follows necessarily. The relativity principle demands superposition, complementarity, entanglement, just like it demands time dilation, length contraction, relativity simultaneity. That's why we have the weirdnesses that we experience. Because it has to be true that no matter who's doing the experiments, where they're at, how they're oriented, how they're moving, they have to get the same laws of physics with the same constants. And so all that weirdness necessarily follows from that fact about the reaction. All right, and then this, our completion then does give us the more unification of phenomena. You have, your electric and magnetic fields unified by the theory of electromagnetism, theories of mechanics and electromagnetism unified by the kinematics of Minkowski space, kinematics of Hilbert space and Minkowski space unified by the relativity principle. All right, so whose meter sticks are shorter? You have two reference frames in motion relative to each other. In one reference frame, you have these three girls, and the other reference frame, you have two boys. The boys and the girls agree with the data contained in these three events. The boys are the same age, so when they partition the events according to their surfaces of simultaneity, events 1 and 2 are simultaneous, and they can see quite clearly that the girls' meter sticks are short. The girls claim the distance between Sarah and Alice is 1,250 kilometers. The boys know it's only 1,000. But the girls are also the same age. So when they partition these events according to their surfaces of simultaneity, it's events 1 and 3 that are simultaneous, in which case it's quite clear that the boys' meter sticks are short. Right? The distance between Joe and Bob is only 800 kilometers, and the boys say it's 1,000. What causal mechanism is shortening meter sticks? None. Length contraction is not a dynamical effect. It's a kinematic fact that follows necessarily from NBRF plus C. Likewise, Alice and Bob make measurements on a triplet state in a symmetry plane at an angle, say, 60 degrees. They collect these data that they agree on is correct. Alice partitions the data according to her +1 and -1 equivalence relation, and it shows quite clearly that Bob needs to average his data to get the plus or minus a half required to conserve spin angular momentum from her perspective. But Bob says, no way. It should be you that's getting a half, right? So when he partitions the data according to his plus or minus 1 equivalence relation, it shows quite clearly that it's Alice who needs to average her data to conserve spin angular momentum from his perspective. What superdeterministic or non-local or retrocausal mechanism is responsible for this average-only conservation? None. Quantum entanglement is not a dynamical effect. It's a kinematic fact that follows necessarily from NPRF plus H. Now, suppose you're like Baldwin, and explanation for you most fundamentally has to be in terms of causal mechanisms. So you're not going to buy into this principal explanation of quantum entanglement. You need some sort of constructive mechanism or causal mechanism. So in his talk here, for example, Great Rift in Physics, tension between relativity and quantum theory, he points out, on the one hand, relativity is understood to imply that nothing goes faster than light. On the other hand, the usual understanding of John Bell's famous theorem is that certain observed correlations between experiments done far away from each other cannot be predicted or explained if no causes go faster than light. Spukhafte Fernwerk Ungen, or spooky actions at a distance, per Einstein. So, Maudlin concludes basically what Bell proved is that relativity can't be right. Which leads Maudlin to believe, one way or another, God has played us a nasty trick. The real challenge falls to the theologians of physics, who must justify the ways of a deity who is, if not evil, at least extremely mischievous. All right, so if you believe a fundamental explanans has to be causal, then you're going to believe Reichenbach's common cause principle is fundamental, and the violation of Bell's inequality due to quantum entanglement is evidence that special relativity is wrong and in conflict with quantum mechanics because there is a preferred perspective on reality due to a deity that is extremely or evil or extremely mischievous, giving us a physics that is hideously incoherent, right? They can't go together. Oh, one of them's got to be wrong, right? In contrast, if you can accept that quantum mechanics is a principal theory providing principal explanation, exactly like Einstein's special relativity, then you can accept perhaps that Einstein's relativity principle is fundamental, and in which case, the violation of Bell's inequality due to quantum entanglement is evidence that there is no preferred reference frame, so the relativity principle grounds both special relativity and quantum mechanics because the deity is benevolent for strict impartiality, giving us a physics that is beautifully coherent. We know where we're placing our bets. Thank you.